Gracias, Enrique. The best.
Okay, good morning. I'm happy to see that you all have a really good energy this morning. So we will resume the Traian's course, training social roles. So I would like to thank the funding provided by both the course, the program of doctorate mathematics from the University of course, and also the research group mathematical modeling and simulation of real mental systems, okay, from the University of Seville, also is contributing to the funding.
Okay.
Thank you very much.
Absolutely. Okay, so once again, so this is for me really honestly, so it's a great pleasure to be here. And so as Tomas said, I think so I would like to thank so the funding that made my visit possible, and also Tomas for inviting me and giving me this opportunity. I think I'm really happy to be here, quite honest. Okay, now, and I want to thank you for waking up early and coming here despite the traffic. All right, so today I will try to wrap things up. I will just remind you what very quickly, like the first few minutes, what we did last time, just to be on the same page. If you have any questions, once again, please ask me, stop me. Yes, it should be more of a discussion. Although yesterday, so some people in the audience, I'm not gonna name names, ask me tough questions. So, but anyway, so ask me questions. I will try to answer those, right, to the best of my ability. When I don't know, and I will say that. And once again, this is not the final answer. I mean, nothing is final here. This is more like up for discussion. This is our view in our group, but right, I mean, this is if you say, look, we should do something different. I absolutely, I'm open-minded. We can discuss that. Okay, very good. So, quick reminder. So, the goal in these two lectures is to present one way of approaching ROM closures and stabilizations. There are many. There's surveys, reviews. Not the book, not so far, but there are many different models. But what is our group, what makes it maybe a little bit different is that we use explicit, so like explicitly, spatial filters. This is different. So I talked about large eddy simulation. This is something that most of you know. We have here specialists, right? And then also I started to talk about reduced order models. And in particular, I talked about one way to use data to find closures. Okay, so this was this part. Now, I'm not gonna go through the first slides. I'm gonna, by the way, so I will send a PDF file. Well, you have it, but I'll send it to Tomas, and you can post that. So I'm not gonna go through the background. Now I can flip through the slides. That's absolutely no problem. This is great. I'm just gonna go to the this is the model that we talked about, in which you find corrections to the usual Galerkin model. So the corrections are in blue. And the question was, right, how to use this in practice? We said that we're going to use physical constraints. So we put constraints on the operators. Those constraints help. We use this model in, I would say challenging simulations. So like the quasi-geostrophic equations right here are chaotic when the Reynolds number is relatively large and the Rossby number is small. So there are issues with the numerical simulations. And then I've shown you like a few slides about using machine learning to complement the model. I got a question last time, I think, it's not this one, it's about this. So you'll ask me this, and it is correct. You're correct. It's the online cost here, right? And there's several developments here. The last one is in collaboration with the Seville group. I said here that you need physics. and we had, you see, so this is one thing that I wanted to emphasize. It is a data-driven model, but we can prove not the same things as in finite elements, in the finite element method, but we can prove important results, like if the closure model here is accurate, then the error is going to be small. I think that's important. Yeah, I'm going to come back to this. And then at the end of the class, we had the pop quiz, and I said, look, we found a model that is accurate, is efficient, and it has mathematical support. I mean, this is the dream for a applied math, computational mathematician. But I said, for commercial software, I don't think that people are, in commercial software, people are going to include this type of models. It breaks my heart. And the question is why? And the reason, I think that this is something we, at least when we teach math courses, we don't emphasize enough. And I think that the reason is very shallow, so it is not easy to implement. You need good people to do that. So my collaborators at national labs, engineers, they actually told me in my face, they said, who's gonna do this? We have engineering codes, we're using Abacus, we have like legacy codes. How are we gonna do this? This is an important thing. So if it's not easy to implement, maybe you can do this locally and investigate the model, but how are people gonna adopt the model? This is an issue. So, okay, that's where we stopped yesterday. Now, today I'm gonna show you a different approach, and for that I need to develop explicitly to talk more about spatial filtering. Now, before we do that, I don't want you to, right? So I don't want you to think that the only thing we can do is the data-driven closure, right? So data-driven closure. That's what ROM closure. That's what we talked about yesterday. This was one done. You can do other things. So like today, in one slide, I'm gonna show you how to. So this is a model that uses approximate deconvolution. This is a technique that is used in image processing. Doesn't originate in the field of CFD. And the idea is simple in principle. It says, look, if you use, right, so it's been used, this idea has been used in LES around 2000s by Adam and Stolz. Right? And the idea is the following. So basically, in a ROM setting, we discussed that what we want to solve is something of the form A dot is equal to plus a tau term, right? Now this tau term, this is the closure model. And there are different ways of modeling this. We discussed one here, the data-driven one. But really, so the point is that this in LES and in LES ROMs, this tau really is, okay, so I guess that this would be minus divergence of, would be U times U bar minus U bar, U bar. Of course, you like to do this with, multiplied by phi and, right, so take the inner product between the two, right? Right? So this is the term that we add here on the right-hand side. And in LES, so this is well known. So the problem, the closure problem is right here, that we don't know what U times U bar is, right? And in data-driven modeling, you just try to fit your different model, right? So would like to express this as a function. That's the idea of closure, as a function of U bar, right? Because U times U, everything bar is not equal to U bar, U bar. So you would like to get an approximation here, okay? So with data, we've seen how we do this with data. But approximate deconvolution goes about this in a different way. So it says, look, you have an approximation W for U bar. So you know that this is W times W, and you'd like to use W to approximate this one as well. So usually what happens in approximate deconvolution, what happens is this. You say, I have some approximate deconvolution function of W that is in some sense approximating the original unfiltered quantity. So that's why it's the defiltering type of approach. Well, if you have that, then you can approximate U times U everything bar by approximate deconvolution of W times approximate deconvolution of W, everything bar. Right? So you have an approximation of the filter quantity, then you can step back, defilter it, and use that in the closure term. So this is approximate deconvolution closure. And this is exactly what I wrote here. Okay, now, so I know that I have only one slide. So this is done, I want to say that this is done by, yes, I'm sorry. Yes. Okay, very good. Very good. So I will get to that. Thomas, this is a good question. So we like this model. Recently we started to use this type of approach for stabilizations with Francesco, but so I'll get to that. It's important actually, and it's unusual. Okay, so one thing I wanted to say is this. When I presented, I want to emphasize this. When I presented the data-driven closure yesterday, I said that that's an LES model, but I didn't tell you what filter we used. I said that we're using a variational multiscale formulation. And I want to say that, yes, it's a variational multiscale formulation. I don't have a filter radius. But you can think of this, so this is, yes, based on VMS, but you can think of this as an approach that uses the ROM projection. Remember, that's what we talked about as, that's what we introduced as a first filter. There's no delta, no filter radius, delta. Please, I want to emphasize this. There's no delta there. However, when we present approximate deconvolution, that's why I wanted to add one slide here. We are using the differential filter. Which has a filter radius delta, right? Right here. I have a pointer. Oops. Right here. Yes, so it's an explicit filter. I want to make this, to emphasize this. We actually use explicit filtering in this. Right. So, okay. Now, so the question is, the question is like, how do we implement this? All right. Now, you see, so let me answer Tomas's question. So Tomas is asking, why do you have this bar here? Well, it's an interesting question. You see, we said that U times U, everything bar, is approximated by the approximate deconvolution of W times the same thing, everything bar. All right. So if I have, so in my notation, so WRAD times WRAD, everything bar, right? And then, right, so that's written, right, so let me write it like this, without, right, so is WRAD dot grad WRAD, everything bar, comma phi, phi k, inner product, this is equal to WRAD dot grad of WRAD, comma, and I'm gonna use my blue chalk, well, green chalk, just give me 1 second, I have green, and I have P K bar. And this was Thomas's question. This is weird. You have a test function and we're filtering it. Well, we can do this because the approximate deconvolution, because the differential filter is self-adjoint. So for the differential filter, yes. Yeah, very good. Yeah. So, yeah, correct. So whatever we use here, which is the differential filter, we use the same thing here. Now, this is very weird. Have you ever seen people using filtered test functions? It sounds like a little bit like Petrov-Belurkin. In finite element, people don't do this, and the reason is that in LES, right? The reason is that you have a lot of finite element degrees of freedom. So computing the filtered test functions will take a lot of effort. However, in ROMs, we have only a few degrees of freedom, or there are. So then it makes sense to compute beforehand phi1 bar, phi2 bar, phi bar. There only are of them, and use those as test functions in the implementation of the approximate deconvolution. This is exactly what we did. Okay, now this is a 10-year-old paper. Once again, we started recently to use that. And it actually, the model works well, but it has the same issues as before. Who's going to implement this, right? So you need to know, right, how to, pre-compute these filter test functions. You need to know how to get the approximate deconvolution approach. So it is complicated. It's a good model, right? We can provide mathematical analysis, but it is complicated. So with this, I close. This is a close. It's a good moment to close the discussion about ROM closures from yesterday. And I'm going to move in a different direction, right? So whatever I told you so far, forget about this, yeah? Because we're going to move in a different direction, which I think is maybe not as technically satisfying, I don't know, so like mathematically satisfying as ROM closures, but it is more practical. So, okay, now, so I will, yes, Thomas, of course.
What my concern is that this kind of filtering,
Yeah,
is mathematically oriented.
correct.
And I don't know up to what extent this dumping of high and higher frequencies is really physical.
Okay, okay, well, it's.
What I'm trying to say is that from the mathematical point of view, you get a regularized model.
Correct.
You get a good mathematical thing.
Correct, yes, we did.
Up to what extent applying this special filtering really makes a good approximation of
Very good.
subgrid scales for a proof.
Very good, very good. So what Thomas is saying, and this is on record, okay, this looks beautiful, mathematically beautiful, but does it work? Is that fair to say? Does the model work? And right, correct. Very good. And I will answer this. Yeah. So for the remainder of the talk, I will show you, I still need to introduce something like, and next I will talk about this delta a little bit. But after that, I will present you simple models in which we use these filters, and they do work in practical turbulent flows. So I'll show you how this works. This is a very good point. And I'll be honest, so we published these papers and the next papers 10 years ago. And at the beginning, I had the same questions. I asked my students to actually look at the signal and then apply the filter and see the ROM signal, the ROM field, and see how these filters smooth out the higher frequencies and or whatnot. So that's how we started. And then we said, okay, they do work, they do work. Do they work when you plug them into the model? And they do work as well. We're very satisfied with those new models. Okay. Okay, but this is a very good question. So, okay, beautiful models, do they actually work in practice? That's what I'm going to show you next. All right. So I'm going to erase all this stuff. because now we're moving from ROM closures, that's what we presented, to ROM stabilizations, really. But they're both based on spatial filters. Now, for the ROM stabilizations that I'm gonna present, both filters, the ROM projection and the ROM differential filter, can be used, and we're using them. But we have a preference for, so ROM stabilizations, and we call these regularized ROMs. ROMs. We're gonna see this in the notes. And there are many, as Thomas pointed out, and so there's a wealth of ROM stabilizations. I would claim that everybody using ROMs for turbulent flows is using some sort of stabilization. There's no way around it. But those that we're using are spatial flavor. They're based on spatial filters. So this makes what we're doing a little bit different. And we said that we're using two spatial filters, the ROM projection and two would be the ROM differential filter. In general, I'm not gonna use ROM in front of this. I'll say differential filter, and we all know what it is. Now, for the differential filter, what we have to do is this. We have to solve identity minus delta square Laplacian times U bar is equal to UR. So this is the input, and this is the output. And one important quantity here is this delta. This delta is the filter radius. All right. So next, for the next three slides or so, I will talk about how to choose this delta. I think that's an important question. And let me pose the question first. This is another pop quiz, right? So, so here's what we have. So I want to find a delta that is physically meaningful. So here's my problem. At the full order model, I tell you what the mesh size is. So like the finite element method to generate the snapshots is based on a mesh of size h. I'll tell you the solution, right? So we find the snapshots, and I'll tell you the computational domain length scale, right? So the length of the domain, this is my domain. Let's say that I have flow past the cylinder, right? So the length of, or channel flow or something like that, right? So the length of the domain is given, the length, the height, and the diameter. So these are given. Okay? Also, I'll give you the dimension of the ROM, the total number of basis functions that you can find, right? So I take snapshots. We discussed this. I take snapshots. And then from these snapshots, I generate a lot of basis functions. Like let's say phi r. So think of this as 100. But I only keep 10 of them, only a few of them. The rest I discard. So I'll give you this, I'll give you this, and I'll tell you what these are. Of course, if I use POD, I give you the eigenvalues, of course, and the basis functions. And here's my question for you. If somebody says you have flow past the cylinder, and you take a model that is 10-dimensional, and if somebody asks you, what is the length scale that you're resolving, what would you say? Right. So the question is this. We take flow past the cylinder at Reynolds number equals 100. Doesn't matter, really. And I tell you that we build a POD, construct the POD, and then I tell you that you build the Galerkin ROM based on the first 10 POD basis functions, phi1, phi2, phi10. What is the length scale that we're resolving? Do we resolve this length scale, all the features that are like this long, this big, or do we resolve the large features, or we go down to the Kolmogorov scale? Do you know? I don't know. Now listen to this. So this is question number 1. Question number 2. I give you the same problem, flow past the cylinder. And then I take a finite element mesh, right? Here like this, unstructured, doesn't matter, right? So some large triangles, some smaller triangles, some very small triangles next to the, right? Next to the cylinder, I have very small triangles. And I tell you, what is the length scale that you're resolving? What would you say? I would say, give me h, and this is the length scale. If I tell you that you do not finite elements, but you do finite volumes or finite differences, it's the same answer. So to me, there is a discrepancy. There's a discrepancy between what you do for POD ROMs and what you do for classical numerical methods. With classical numerical methods, like finite element, you always know the length scale that you're resolving. It's h. With ROMs, a simple question like I have 5 basis functions, what is the length scale? Or I have 100 basis functions, what is the length scale? You cannot, there's no clear answer, there's no immediate answer, right? Right? So this is the question that we're trying to answer, and this is important to us because we want to define the filter that has a radius that is meaningful, is physically meaningful. I would like to say this is, right? So some people told me, I was told, well, last year's, right? So it was a conference in Barcelona, Atmos. I gave a talk and somebody in the audience said, oh, what's the big deal? You just choose H. But you see, that's the problem. Because you choose H, so you do a ROM that depends on 10 basis functions. And then with the same finite element method, you use a ROM that uses 100 basis functions. Well, this should have different length scales. You cannot say that this is H and this is also H because they're not resolving the same length scale, right? They should be different. You change the dimension, the ROM dimension, you change the length scale that you're resolving, right? But this one stays the same for both of them. So I don't think that using H here, delta is equal to H, I don't think it's a good idea, right? So delta scales like H. This is a lot of people, even we, like long time ago, that's what we're using, but I don't think that that's the right thing to do. Okay, so how do we do it? So I have a proposal. I'm going to show you what I mean, and then we can talk a little bit about this. So what is the principle? We're saying the following. We're saying that I'm going to denote with capital lambda the ratio between the eigenvalues, the sum of the eigenvalues from 1 to little r, so those that you keep in your ROM, over the total number, the sum of the total number of eigenvalues. Okay? So if we keep only 10 modes, this would be a sum from 1 to 10. And then if the total number of modes is like 100, then this would be the sum from 1 to 100. Now, the sum of eigenvalues, as we all know, represents, the sum represents the total kinetic energy in the ROM. So this, to me, would be the kinetic energy of the length scale delta that I want to define. But if you keep all the eigenvalues, that means that you pretty much keep all the information in the snapshot. So this would correspond to the kinetic energy of a length scale that scales like the FOM length scale, which is little h. With this in hand, we said, okay, assuming that everything is like following the, the Kolmogorov statistical theory of turbulence. So this is an assumption, a big assumption. We said that the kinetic energy of the wave number k is the integral of the kinetic energy content. We assumed the Kolmogorov scaling argument. We plug this in these two formulas, and then we got the formula corresponding to the delta 2 and little h, right? So we connected delta and little h to the corresponding wavelengths. Right? So I know that here we have k, wave numbers, but there is a relationship between k and wavelength. Okay, we plug this in and we got a beautiful formula. I think it's a beautiful formula. So we said, so according to that relationship, we said that delta scales like capital lambda to h to the 2/3 plus 1 minus capital lambda times L to the 2/3, everything to the 3/2. I'm going to write this down and I'll tell you why I think that this is a nice formula. Then I'm going to show you some results and we can discuss this. So we said that our energy length scale is equal to capital lambda times h to the 2/3 plus 1 minus capital lambda capital L to the 2/3, everything to the 3/2. So I think that this is a nice formula because of the following reasons. So capital lambda, let me remind you, is the sum from 1 to r of the eigenvalues over the sum from 1 to capital R of all the eigenvalues. And I want to emphasize what happens in the asymptotic regime. So when little r goes to capital R, lambda, capital lambda, goes to 1. Well, when lambda equals 1, this term disappears. This is 1. So you have h to the 2/3 to the 3/2. So delta 2 here goes to little h. It makes sense. If you take more and more basis functions, then you expect to resolve the entire spectrum, which means that you basically are doing a full order model. If you take all the modes, that means that you're doing the same thing as the font. And we get that. Now, if you go in the other direction, r is equal to 1, then lambda is almost going to 0. This term disappears. This is 1. So you get capital L, which is the dimension of the domain. So it means that if you take one mode, the best you can hope is to resolve a length scale that is like the scales like the computational domain. So we thought that this is interesting, and then we tested this in numerical, the turbulent channel flow. We got good results, and I'm just going to show you a table. So this is our energy length scale for different R values for turbulent channel flow: 4, 8, 16, 32, 40, and 50. And you can see that as we increase R, our delta decreases. And that's what you expect. You take more and more basis functions, the length scale should decrease. However, the only other length scale that I know of, that's Lumley's, the famous John Lumley, right? Length scale, that's based on dimensional arguments. And the point is that this one, as you change R, pretty much stays the same. So the advantage of what we're doing, I think, with this energy length scale is that we developed a length scale that it is asymptotically correct as you increase or decrease the dimension of the ROM. Okay, so this is our favorite delta, filter radius. But you can take delta equals to a constant. You can find it from actual data, like data-driven modeling, and we're going to talk about this. The point I want to make is the following. So to present these models, I said I need two tools. So we need the filters, and the tool that we devised, discussed so far, the ROM projection, done, and the ROM differential filter. I had to tell you how we find the filter radius, and I've just done that. So now we have the filters. Let's see what the models are. Yes, Thomas. You're right. Correct. Right. So we assume that that's a very good point. So to use this type of formulas, you have to assume that you're in the inertial range. And this is a good. That's true. That would be that's a very good point. And in fact, there is right. So when we write this right here, now I can ask, what does it mean R goes to 1? I mean, so is R is equal to 1, right? What I meant is when R goes to 0, we'll never get to 0, right? So this has to be taken with a grain of salt. You're correct. But okay, right. So, right, because I said R goes to 0, then lambda goes to 0. But this is not quite true. You always have a lambda that is strictly greater than 0. And you're correct. So it shouldn't be the capital R. The capital L should be the length scale given by the inertial range. I also got questions about, yeah, but you also assume a homogeneous isotropic regime, which is true. And now when you work with the bounded turbulent flow, like the turbulent channel flow, this is not quite like that. So then the question was, Masayano asked this question. So what do you do near the boundary? Now, near the boundary, we cannot use this. Right? We cannot use this stuff. But then my thinking is that maybe instead of this, we can use boundary layer theory or something of that sort. Right? So right, that is correct. So this is a very idealized situation, working homogeneous isotropic flows. We should define these length scales based on that inertial regime. And then what happens if you're not there? That's a good question. We haven't done that. Yeah, but my point is that despite this, I think we're doing significantly better than what's on the market. That's what Lumley does. Right, based on these dimensional arguments they're even more optimistic than ours. And you see in practice, when you plug things in, these values in, he's getting results that actually physically do not make too much sense. So we do better than him. Okay, I'm not saying it's perfect. I'm just saying it's better than what else? I don't know of any other length scale used in ROM. If you know, let me know. Okay, so now it's a good time to start presenting those models. This was Tomas's question. Yes, these are beautiful models, but how do they work in practice? That's what I'm gonna discuss next. I think that's very important. So the first model is in the class of regularized models. So filter-based stabilizations is a very simple model that we introduced 9 years ago. We extended this from classical numerical methods, and it is a model that works and it satisfies all our criteria. Okay, so what does this model say? It's very simple, and that's why practitioners like it, and we like it too. So it's called evolve, filter, relax, and it's a very simple approach. So it has 3 steps. It's made up of 3 steps. In the first step, you use your ROM code, whatever you have, whatever time discretization you have. I wrote this for Euler, but if you have Crank-Nicholson, if you have anything else, you can use it, no problem. Huh? So you take your code, you know your ROM approximation at step n, and you want to find the ROM approximation at step n plus 1. Okay? In the first step, evolve step, you just use your current code to find an intermediate approximation, Wn plus 1, right? So it's right here. Okay? This is the Galerkin ROM that you use to find an intermediate approximation Wn plus 1. Yeah? Whatever code you have. So it doesn't have to be for Euler. It can be anything else. Then that's the critical step, the filter step. In the second step, you take this intermediate approximation and you filter it. Yeah? Yes, just a second. In the third step, we relax this approximation. So we take the filtered velocity, scale it by chi, and then we take the unfiltered, the original one, velocity, and we scale by 1 minus chi. So this is a convex combination. of the two. If chi is large, then this one, so chi is equal to 1, then this disappears, and then you're just using the filtered field. So this is a lot of filtering. However, if chi is zero, then there is no filter, and that means that you're using the original process. So this would be Galerkin. So chi equals 0 means Galerkin, chi equals 1 means only filter. And if you take chi equals 1/2, you do something like Traian-Nicholson. You do a little bit of filtering, a little bit of original field. Yeah. So this is the step. This is the procedure. It is trivial, and I will talk a little bit about this. Be good. Sorry. Yeah. Yeah. Correct. That is correct. That's correct. Okay. So I will present other models first of all. So this is just model number 1. I have 3 models. I'm sorry. So I have this one, I have the Lorraine model, and I have the time relaxation model. And those do different things. But Birgül made a very good point. So is this LES? And this is a good question. So in fact, you can show that for explicit time discretizations, this is actually, if you use the differential filter, this actually introduces eddy viscosity with a certain coefficient. But this is not necessarily true if you use an implicit method, and that is not very clear. So yes, it's a stabilization method, and yes, there are connections with closure models. But you're correct, it's not exactly a closure model. And you're also correct that for this particular model, we filter entire field. But this is not true for the next model, array. Yeah. Uh-huh. Okay. Yeah. Okay. Yeah, that's a good question. So how do you choose chi? And you know what? So this is a good question, and I like that. But here's my counter question. So if you do machine learning, how do you choose those parameters? I mean, right? And I have one parameter, and people give me a lot of, like they ask me a lot of questions. How do you choose that? How do you choose 1 or 2 parameters? You have in machine learning, you have like millions of parameters. How do you choose those?
Is this parameter universal or problem dependent?
Okay, this is a good question. So, in fact, I have to this morning, no, last night. Last night I did an important slide that answers this question in a nice way. And we cannot do this in general, but I'll show you how to use numerical analysis. And I think that that's a difference between this and machine learning. Have you seen numerical analysis using machine learning to determine parameters? I haven't seen that. But parameter scalings, that's what you're asking. I think that these are important in numerical analysis. That's exactly, I think, in my opinion, this is the right way to sell numerical analysis. Yeah, so I'll show you that. Very good. These are good questions on that. But now, so 3 steps. These are 3 steps. And what I want to emphasize, I don't know if this is almost non-intrusive. If you give me the Galerkin code, in the first step, I just push a button, right? So I go 1 step. There's no, personally, I don't have to modify the code. Fair? Yeah. In the second code, you say, I take this output and I filter it. And you can say, oh, but how do you do that? Well, if you use the ROM projection, which we've done in the past, there's nothing that you have to do. You have to zero out the coefficients from 11, 12 to 100. That's all. If you use the differential filter, then you do have to solve an r-dimensional linear system. But this is modular. You don't have to modify the code. You just add a subroutine. You just add a different, a little thing. A graduate student, let me put it in a different way. A graduate student, if you give the graduate student the stiffness matrix here, should be able to actually do this in half hour. If the stiffness matrix is provided, you choose a delta. Like how you choose delta is, that's an important way, but it's a scalar. You choose that, then you can solve the linear system, you're done. It's an R-dimensional, low-dimensional system, not a large system, low-dimensional system. So I would say that this is the computational implementation of this is trivial. That's the difference, practical difference between this and fancier models. Okay. Now, so embarrassingly easy to implement, trivial, and it's almost non-intrusive. Yes, you need the steepness matrix, but yeah, I mean, you should be able to access that. Yeah. And if you don't have the access to the steepness matrix, use instead the ROM projection. For that, you don't need anything. You just zero out the coefficients. You don't need any to solve anything. Yeah. So we like this. It's a very simple model, but Tomas's question still stands. Is it working? Is it a good model? Yeah. So we're gonna talk about this now. Let me answer Virgil's question. Very good question, which is, well, you're filtering the whole thing. It is correct. For evolve, filter, relax, we filter the entire field. But we also looked at this different approach. This is called the Luray model. And in the 2000s, in LES, there was a strong push for models like this, so no ROMs, by Foyash's group. So Foyash, Titi, they call this Navier-Stokes alpha. It's the same idea. Okay, just want to emphasize. I like Luray because this model was really proposed by the great French mathematician Jean Luray in 1934. And you know how many computers were in 1934? 0. Jean Luray did not use this, did not propose his model for like computations or whatnot. So he was trying to prove existence and uniqueness of the turbulent flows, solutions of turbulent flows. So that's what great mathematicians do, like, come up with models that people are going to use 100 years afterwards. Really, really impressive. So it's a simple model. So what do you do? So basically, you know this, but okay, so you take the Navier-Stokes equations and you regularize them. And to regularize them, you see the Virgil. So this is addressing your question. We're not regularizing the entire field. That's different. We're regularizing only the U component in the nonlinear term, the first component in the convective field. So in other words, right? So let me erase this. I'm going to erase this, and I'm going to show you what I mean by that. And it is an effective model. Maybe it's not the best model, or people ask what the best is, and I really think that this is problem dependent. But all right, is this? So we have the Navier-Stokes equations. So we have U sub t minus Reynolds inverse Laplacian of U plus U dot grad U plus gradient of t is equal to f. Now, divergence of U is equal to 0. Now, what Luray did was very simple. And he said, let's filter this U component. So we have U bar here. By doing so, the solution turns out to be smoother than the original solution of the Navier-Stokes equations. And that's exactly what we're doing here. So this is a model, once again, introduced in the same paper. We're using the same paper. This is the Galerkin ROM, in which we filter just the convective field. What does it mean? So this is intrusive. This is not as non-intrusive as the EFR. What we have to do is, when we look at the tensor B, we have to modify it by filtering these components. So basically, you see, for the Navier-Stokes, the G-ROM, I should say, for the Galerkin ROM, we have that B I J K is equal to phi dot grad of phi j phi k. All right. Now for the Luray model, Luray ROM, we have that this B bar of ijk is equal, by definition, to phi I bar grad of phi j comma phi k. So the person who's implementing this should be able to change the implementation from phi I, which we have here, to bar phi I. Right? That's the difference. I mean, it's not a big thing, but it does require knowledge of the code. Yeah. So this is the second model, array RAM. I'm gonna come back to this and right. So yeah, questions? We have questions now. Okay, very good. The third one is something that is so we introduced this last year. We looked at this last year. It took us a while. But this is a model that is more akin to the closure problem. So you do use the Galerkin ROM, but you supplement it with a stabilization term. This one turns out to be a stabilization term if you use the differential filter. So you take you have a chi, the relaxation parameter, and then you add the u minus u bar term. The effect of this turns out to be the elimination of the filtering of the higher frequency. So the frequencies that are close to the cutoff frequency. You do not filter that much the low frequencies. You filter mostly the frequencies close to the cutoff. So what time relaxation is trying to do is to get you something like a sharp cutoff filter. This was used in LES. This was used in conjunction with the proximal deconvolution as a sort of extra stabilization. And it's used after that. It's been used in LES again by itself independently as a stabilization term. And that's the approach we're taking here. We use this as an extra stabilization term, which is based again on spatial filtering. Everything that we're presenting, all these three models, EFR, L'array, time relaxation, are based on spatial filtering. All of them. All right. Okay. So, do these models work? That was, this is, so first of all, okay, like at this point, I have to say, so I would say that the biggest difference in my mind between these regularized ROMs and the closure ROMs is that just comparing them, just looking at them, is that these models, the regularized ROMs, require much less work to implement, much less work. I would say EFR is a zero cost in terms of implementation. You cannot say the same thing about closure models, data-driven or actual, mathematical, physical closure models, like approximate deconvolution, like Smagorinsky, like Ladijenska, or, these kind of models require knowledge of the code, so they're quite intrusive. These are, like, especially the EFR. EFR is zero intrusive, right? Right here. There's nothing there. Modular. So the question is, okay, they look better. We did prove, we do have numerical analysis results, but the question stands, do they work in practice? Now I'm gonna show you one example that pretty much answers this, in my opinion, pretty much answers this question. So this example is for EFR, but I'll show you results for the other test cases, for the turbulent channel flow. And the top and the left are what I presented last lecture. I said, if you use LES to generate the data, this is expensive, very expensive. And then you take those snapshots and you consider the POD modes and you consider a 100-dimensional Galerkin ROM, what you get is garbage. 100-dimensional Galerkin ROM for the turbulent channel flow, in our case, is garbage, which is very bad. But then, if you take an 8-dimensional ROM, so not 100, you take an 8-dimensional ROM, and then you do a little bit of filtering, like in EFR, you get something that is not exactly LES, but is much better in terms of quality than the 100-dimensional no filter model. to me, this shows that the approach is effective. It shows that with minimal computational effort, you can actually fix, if you reduce the computational cost dramatically, and you fix the issues with the standard formulation. This is the type of things that engineers like. They want to see easy fixes that can be physically, they can interpret physically. You know what the differential filter is doing. You can see it. It's not just a parameter that don't know its meaning, right? So you know that you're using a smoothing type of procedure, and look, it does work in a challenging. The turbulent channel flow is, in my opinion, is the most challenging test problem that I know of for turbulent flows, for ROMs. And this is effective. Okay? Right. So this is when I give talks, I don't usually give so many, I don't have so many slides, but this is one of the slides that I usually use because practitioners like this type of results. Okay, now you can say, okay, Traian, but what does it mean in terms of statistics? Visually, I understand, but what does it mean in terms of statistics? So like here, I still present, so this is not a statistic, but I'm looking at the time evolution of the kinetic energy. And if you use the 100-dimensional ROM, it blows up. But if you use this EFR easy filtering, you can see that you don't get perfect results, but you do get a stable solution. And actually, if you look at the second order statistics, obviously, you get much better results than the 100 with, so the 8-dimensional ROM in blue gives you much better results than the 100-dimensional standard ROM. This is effective. This is for the turbulent channel flow, but Reynolds tau 395. It's not 180, but it's not 590. It's 395. It's a with, so I forgot, right? So with 8 modes, 8 POD basis functions. This is effective. Okay, now, so I told you that I'm gonna show you results. I don't have a lot of slides, but I can show you results for, so we do have results for, we have many papers and we have results for all of them. But what I want to show here is we compare these models. We compare the time relaxation, ball filter relax, and the ray ROM. We compare them in terms of statistics. So first we looked at the Reynolds normal stresses and then the shear stresses. So these are U prime, and these are U prime, V prime. And we also looked at, the optimal parameter. So in terms of second order statistics, in our investigation, JCP 2025, it looked like the time relaxation actually gave better results. I'm not saying that this is always always true, but the turbulent channel flow investigation, comparing second order statistics, the time relaxation model did quite well. So this is a model we like. Now, you can criticize that. Yeah, so in terms of accuracy, the time relaxation looks better in terms of second order statistics, but I want to remind you that you do need some sort of intrusive implementation. So I don't know. If I'm an engineer and I don't want to spend too much time doing this, I would probably use something like EFR. Because it's still effective. If, on the other hand, I want more accurate results and I can spend time implementing the model, then probably time relaxation would be a better choice. Yes, Virgia. Yeah. Here, there's a, yeah. Correct. So I have not talked about the last 2 slides. I only talked about the top slides, so this is a good point. But the last two slides are actually very important in my opinion. And these slides say something different. So they're not talking about accuracy. They're not talking about which model is better, is best than. So these models talk about a question that is not usually addressed. And this is, you see, every time, let me show you something. So if you look at if we go back to the EFR model, so this model, maybe I went through this very quickly, but this model actually has two parameters. One is chi, and this matters. Like how do you determine this parameter chi? And the other one that it's implicit here, so is the filter parameter, right? What is delta, right? So there are two parameters here. Now, if you look at the Leray model, this one does not have a chi, but it does have a delta parameter. And then finally, the time relaxation model again has two parameters. One is delta, and the other one is chi. And the question is, how do you choose them? And in this plot, we looked at finding, and it's written right here, finding the optimal filter radius. So we said, you know, for a fixed chi, how do you find the optimal value of delta? It was like machine learning pretty much. We just looked at the different values. We investigated different trial and error. Look at different values. Let's find the delta value that gives the best results. And we did this for different dimensions. This is, and that's what the notation we use in the paper. It's R. Yeah. In my notation, it's R. So 10, 20, 30, all the way down to all the way up to 100. And what I want to emphasize is that the filter radius, the optimal filter radius for different N R values is the same. Or it's not the same, but it is around, it has around the same value. Yeah. So for different curves, we got the filter radius that yields the least error. So we get one value for the blue curve, another value for the red curve, another value for the green curve. I mean, the minimum is not exactly the same, but is located around in the same area. So this is a good result. It shows that there is relatively low sensitivity to the optimal parameter value. Of course, at this point, this is not a mathematical result. It's just trial and error. So I cannot guarantee that this is always going to happen. But based on our numerical investigation, it looks like the parameter, the optimal parameter value is robust. And furthermore, we did this in the reproduction regime, so like the training regime. And then we moved to the predictive regime. And we got qualitatively similar type of results. The optimal value for the filter radius doesn't vary too much with the dimension of the ROM. And I think that this shows the robustness of the procedure, which was very, very encouraging. I mean, so yes, so it is the error, right? So for different values of delta, we computed the error, and then like for each, right? So let's see, this one, the orange maroon one. So this reddish one represents the errors for different delta values. And of course, you would like to choose the delta value that yields the minimum error. So it would be this one right here. Now for the green curve, that would be n is equal to 60, different value. Of course, we again choose the minimum value, and this is different from the orange minimum value. Correct, yes. Okay, so in this particular investigation, we use DNS. Now, okay, so I actually have overall in our group, to compare our results, we use both DNS and LES. For this particular, Samuel, you're correct. For this particular one, we use DNS. But I actually, so if you use DNS, this means that your results can be trusted, because, right, I mean, this is the absolute benchmark. The question, though, that I got asked in the past, and I agree with that question, is how realistic is that? Yes, we can do DNS for the turbulent channel flow, but how realistic is that if you want to use this in an engineering application? You cannot do DNS for that. So I think that actually the more relevant, maybe not as accurate and trustworthy, but more practical setting would be to generate your data with LDS, or even better with RANs, or some stuff that engineers use. Of course, the snapshots are gonna be noisy and inaccurate, but that's life when you talk with when you do turbulence. So I think that those results would be, you could maybe you should trust those results with so the uncertainty in those results is much higher than the uncertainty in these results, but that's more realistic. Like here, you see, here we used LES as our benchmark, so that's different. That's more practical. Here, however, we use DNS. It's a good point. Yeah. All righty. So we've done that. Now, so one thing. So let me raise this. One thing that, and with this, I'm gonna maybe. Okay, I'm gonna erase all this stuff. Any questions? Do you have any questions for me? I want to say one more thing about the numerical analysis, because I think that this is important. And this is something that Thomas asked me, and Bigul, and I want to yeah. So numerical analysis. And I want to take some time to talk about this. Numerical analysis for regrams, right? So, okay. Any questions so far? No? All right. So once again, so what we've done so far, we use filtering, but now to develop closure models, to develop stabilizations. They do work. I hope that I convinced you that they work in challenging. To me, turbulent channel flow is the most, I really believe, under-resolved turbulent channel flow, in my opinion, is the most challenging test problem for ROMs in turbulence. It is very tough, because in fact, some of the models that we like don't work. So you have to fix those. I said this last time, and I stick to that. So, okay, now, so the results are encouraging, but there's one thing that maybe is a little bit, so the question I got asked last time, and it was, oh, by the way, so there was a question in the chat, maybe from Bosco, saying, how does AI compare with your models, right? So let me remind you. So the first lecture, we presented data-driven ROM closures. And today I presented an approximate deconvolution, so mathematical math ROM closure, the data-driven one. The approximate deconvolution of. This is the VMS, data-driven VMS. Okay. Very good. And the question was, if you compare this with AI, machine learning, why not use this? And the honest answer is, yes, you can use machine learning. You can use machine learning to replace everything that I've shown you before. There is, however, a difference. Maybe I didn't emphasize this last time, but for all these models, most of them, we have mathematical support. And I had a discussion with Birgul yesterday, and I want you, for mathematicians, this is fundamental. But when you talk to practitioners, I want to warn you, be careful about these statements. Because I was told, so my usual argument is this: we have mathematical support And what I mean by this, in my mind, yes, at the continuous level, but for ROMs, I mean numerical analysis. I want to discuss this. So numerical analysis. What do I mean by that? And this is something that this is one of the strongest groups in terms of numerical analysis of ROMs and closures and stabilizations and LES for older people like us. All right. So numerical analysis. So what does that mean? So the first thing that we take for granted, but this should be emphasized, is stability. That's what Thomas was talking about. We were discussing yesterday. The second one, and I think that this is important as well, is convergence. And when I say stability, I want to say that my ROM solution, UR, is guaranteed less than or equal to a constant that depends on the data. You give me the data, I compute the constant, if I can, then I guarantee you that the solution doesn't blow up. Convergence means something different. So you take the difference. I mean, I know I'm preaching to the choir here, but I want to be on the same page. So U minus UR, and this is a little bit delicate. So this is less than or equal to a constant that doesn't depend on the discretization. Usually, we have a ROM discretization error, and this is the new part. But we also have a finite element or form error. And we also have, I'm going to write it here, but maybe you cannot see it, a time discretization error. Like if you use Crank-Nicolson is second order, if you know, things like that. Yeah. So this is classical. The delta t, right? So this is delta t to some power. So P3. Yeah. This is pretty classical. And I will circle this and leave it here. Usually, this is what Kunisch and Folkvine, the original papers in 2001, that's what they insisted on. Okay. The ROM solution, the ROM error, is right here. And for this one, usually instead of delta t, you have something like sum from j equals r plus 1 to capital R of lambda I. If it's in the L2 norm. If it's in the H1 norm, you have times the norm of Pi in H01. Okay? This is that. You have terms like this, but it also have things like, if you use the inverse inequality, the L2, the 2 norm, matrix norm of the stiffness matrix. That's another thing that shows up. Okay, that's also pertaining to the ROM error. But you see, there is there is something that is not always like, for example, Kunisch and Folkvine never took this into account. You also have the finite element there, and this is also h to some power p2. So you see, these two you always have in the finite element formulation. These you don't have in the finite element formulation. And the errors that we're getting are always a combination of all three types of parameters. Time, obviously, space, finite elements in space, and ROM. Okay? And the point is that you want convergence. What convergence means is that when delta t goes to 0, h goes to 0, and little r grows, you would like your solution, your error, to go to 0. Right? So these are convergence results. That's the numerical analysis. Now, I think that we're preaching to the choir. Maybe this distinction is a little bit subtle, but okay. So you guys know this better than me. But why am I emphasizing this? Because when people talk about mathematical support, I hear statements like, yes, you have mathematical support for AI. And this blew my mind. I mean, how do you have mathematical support? Because you never prove convergence for machine learning. Very rarely you do that in special situation. Stability maybe, so that's a little bit more delicate because they usually say we have constraints, we're using physical constraints, and maybe you can prove some sort, you can rely on some sort of stabilization. But what I want to emphasize is that, and I'm not saying that this is true, but sometimes people in AI, many times, think about mathematical support as UQ, uncertainty quantification. They say, I tell you how the uncertainty in the system is propagated by my machine learning model. And they say, I have mathematical support. But my point is that this mathematical support, this UQ, does not tell you anything about results like that. You cannot guarantee that if you take twice as much data, your error is going to go down by a factor of 2 or 4 or whatever. And the same thing for, like, if you take twice as many basis functions, you're going to reduce the error by a certain factor. So this is different. What we're doing here, what we're doing in this setting is different from UQ and is different from what people, vast majority of machine learning models can prove. This is one big advantage. Now, are people going to buy this, practitioners? So if I tell them that I can prove stability and convergence, are practitioners going to buy this? And this is a very delicate question. I know that in our groups we prove this kind of stuff and we publish these results, but have you ever gone to a practitioner, an actual engineer, and say, look, because we can prove this, we think that our model is better? Did they say, oh, okay, yes? It is a hard statement. I know I'm recorded right now, but you know, in my experience, they're not like really, I mean, this is not as important for them as it is important to us. And I would say this, engineers will probably use a model, machine learning model, even though you cannot prove anything about it. I would say this. That's the ugly truth, right? So the good question, does it make sense? I mean, I'm just saying, right? So the good question is, how do we sell what we have? And in the next slide, I'm going to show you one way to sell this. This one is not going, oh, all right. Very good. I think, so in our group, we've been doing this for a while, and recently we started to push this very, you know, farther and farther, harder and harder. I think one way of selling what we're doing is by saying that we can actually prove parameter scalings. And this is a question that Virgia was asking. So here's the one slide from a recent paper with my 2 postdocs and Giulia Novo from. So she provided some help with the spectral element formulation. We said, Giulia, can you help us? And she did. So here's what we did. We proved an error bound of this form. And this error bound had all 3 components, time discretization components. But based on these error bounds, we found scalings of chi with respect to the parameter r. Okay. You can think of this like, so think about SUPG. In SUPG, right, what do? You have a stabilization parameter and you say, well, but I don't know, how do I choose this? Well, if you look at the size of the terms in the bound, you can actually balance those, and you know, with certain assumptions, you can get a formula like delta tau, the stabilization parameter, scales like little h, right? That's very useful. I don't think we appreciate it in finite elements how useful this is. It's not perfect. You can do better, but it is a scaling. And the question is, can we do something like this for ROMs? And we did. And here's how we did. So we said, well, I have, with the triangles, I have what chi theory, so this is the scaling, the parameter scaling should be. And you can see this curve with triangles. But then we took a numerical, very computational oriented approach. We said, can we find the optimal chi? Let's see what this is. And the optimal chi effective, is done with the blue blue circles. You can see, if you compare these triangles with the blue circles, that means there's one issue here, but other than that, I would say that the curves are very similar. They have a similar trend. Of course, this is great. Of course, this is a parameter scaling, so they involve like constants. So what we did, we took the 4 numerical values, we calculated those, and then we estimated the constant, the scaling constant between these 4 values and the first 4 values in the triangle curve. Then we took that value and then we extrapolated. We know the triangles. We estimated the constant, the difference between the two. So then we extrapolated, right, with respect to R with the red cross. You can see that these red crosses, with these exceptions, so this is what, 24, I forgot what number this is, but most of them are pretty close to the optimal numerical values. What does it say? To me, this is a very powerful message. It says that if you have numerical analysis support, you can use that practically to find scalings that you can actually use to extrapolate. This is in complete contrast with what people do in machine learning. In machine learning, you run your model many, many times to estimate the best values for the parameters, right? Well, numerical analysis, math, can save you all this computational effort. So this is one way to sell what we're doing. And I think is important, is not appreciated by people like us in general who work to improving numerical analysis results. And I think it should, just like in finite element methods. Because if a machine learning person, that's how this discussion started. If can AI be used? I mean, quite honestly, yes. If you're willing to devote all this effort to computational effort to find the best parameters, yes, I think machine learning can replace both closures and stabilizations. What they don't have is this robustness, and they cannot prove anything. And you can say, oh, but who cares? Well, here, you care because you save a lot of computational effort. So I think that, and you can trust your results. You can trust that by using twice as many basis functions, you reduce your error by a certain factor. That's trustworthy. That's in contrast with the AI models. Okay, maybe should we take a break, a 5-minute break? But I don't know. It's up to you. I mean, or we can just finish. We can finish, yeah? Okay, very good. So, any questions? No? Okay. So I guess you don't want to go on record criticizing me. You want to criticize me after the... What are friends for? I like that. Okay, very good. All right. So, very good. Sorry. Now, I want to really move on to something that is, well, if I can, it is very close to my heart, and this is the most exciting part of what we're doing. But just to summarize, so we've done a lot of work with the regularized ROMs, especially in the last few years. So Maria and Francesco and right, so the CISA group. So we looked at model consistency, control. We did the proximal deconvolution. This was Francesco's. So he pushed this idea. We looked at variational multiscale with Tomas and Maria. So that was a very nice paper. We really, I think that this is a good idea. This was Tomas's idea. I'm always honest. You know, I don't want to take credit for this was Tomas's idea of combining the two. I never thought about this, and I think it was a very good idea. And then this is something that you're asking me, like how do you choose these parameters? And I've shown you one way, which I like, which is numerical analysis. I really believe in that. But you know, so there are different, maybe more practical ways, and this would Ana Ivanes and Maria Satsuro thought about using machine learning to do that. So you do some optimization along the way to find the best value. You cannot extrapolate. You cannot say it's always gonna be the case like we did with our numerical analysis approach, but it is effective. You can find the best parameters by using machine learning. And this is the part that I was trying to emphasize is numerical analysis. Yeah, I really think that there is value in what we're doing, and we need to sell it better. And I think parameter scaling is one good way to sell it. Okay, all right. This concludes the filter-based stabilization. Let me remind you that yesterday we did filter-based closures, done. Today we did filter-based stabilizations, done. And drum roll, next for the last 20 minutes or so, I'm going to tell you that forget absolutely everything. So forget about all the filters. So like for 20 years, I've been trying to use filters in LES, in you know, stabilizations, in ROMs, and now I'm telling you forget about filters, right? You know, an old guy devoted his life to this, and then he says no more. Okay, so I want to present a new idea. This is really different, a different idea. This is a data-driven stabilization operator. We call it StabUp. We're really happy about. I'm very excited about this, and I think that this is the way to go. Right? Personal opinion. This is the team. This is Ping Xuan. He was the leader of the project. He's my postdoc. Fortunately for him, unfortunately for me, he's moving on. And this is Ana Ivanes, my colleague Annalisa Quaini from Houston, and this is Gianluigi, right? So Ana is Gianluigi's student. Okay, now this has not been accepted. It's on archive. It's been, so we had a minor revision. We answered those questions, and it should appear in Kamami soon. Okay, so this is an actual paper. You can download it from archives. Okay, so filtering. All right, so it's good. Closure, stabilizations, but they're open questions. And some of them you asked me. Yeah. So if I give you an unphysical solution, and then I use a filter to eliminate the issues in this unphysical solution. If I choose the optimal filter, that's what you're asking, Virgia. If I choose the optimal filter, I get good results. That's what I've been telling you so far. However, if I do not choose the optimal filter, I might get, most of the time, I get unsatisfactory results. For example, if I take a very small filter radius, that means I'm not filtering a lot. So then these values are maybe a little bit better than this, but it's still ugly, right? So this is unphysical. On the contrary, if I do too much filtering, and that's when you have evolve, filter, relax, that's what the relaxation step is trying to do, to limit this over filtering. But if I do that, I also get bad results. So you see, it's not that filtering always works. You have to find the right parameters for the filter, the optimal parameters. Okay, so what are those? And let me ask you a different question. So if I want to filter, which filter do I use? Do I use the differential filter? Do I use the projection filter? Or in LES, do I use one of the many filters, Gaussian, sharp cutoff, whatnot? Once I choose my filter, how do I find the filter parameters? That's another question. So you see, filtering is good, but the decisions that you have to make, and for each problem, you may make you probably will make different decisions, right? You choose different filters, you choose different parameters, right? So this is an open question. And this is the motivation for our approach. This is weird. This is think outside the box. The question is, do we really need spatial filters? And as somebody who wrote books on LES and review papers on combining LES and ROMs, this is a crazy question. Do you really need filters? Of course, 20 years we've been using those filters. But I'm not so sure anymore. So the whole idea is in this box. Our idea is to turn the problem on its head and say, instead of using spatial filters, we know that they work. If you choose the parameters carefully and the filters carefully, they do work. I hope I convinced you. If not, LES people are convinced about that. But the question is, can we do better? So this is the way we look at the problem. If you have issues with your under-resolved simulations, you know that if you use a filter, you get better results. That's clear. But the question is, can you do better than that? And our original answer was, yes, we think you can do better. So here's what we decided. I will illustrate this very quickly. So I know that I'm almost there, but this is not going to take, I'm just going to show you results. And, we're almost there. Hang in there because I'm almost done. So this is the principle. This is very important. I'm going to stay on this slide until we understand. So the principle is this. So look what we did for Luray-ROM. Look at Luray-ROM. We said that we have U sub UR, partial T, VR, plus Reynolds inverse, gradient of UR, gradient of VR, plus UR dot grad of UR, VR is equal to times VR for all VR in XR. Okay, now if you, and we are doing regularization, this is the Luray model. All right. So another way to look at this is to make the following statement. If you take the standard Galerkin ROM and you choose one particular piece of it, it's not that we do this for the whole model. So this is GROM. It is GROM. And this part here is just a little piece. It's not the whole thing. It's just a little piece. The way I would describe this is that if you modify this little piece from the standard ROM, you get better results. Yes, of course, you do this in a specific way, use a filter. But the good question is, what if you use a different type of operator? Luray's idea in 1934 is to use a filter. I get that. And he improved the results, right? But what we could ask for a given setting, can you find a data-driven operator that is better than the filter? That's the question. So, with this in mind, we said, let's look for a mapping from the ROM space to itself, right? A mapping that is parameterized by this parameter vector, such that if you give me the coefficients of your ROM input function, this mapping is going to spit out, is going to provide coefficients AJ bar. Sounds like a filter, but it's not necessarily a filter, right? And the question is, how do you choose this mapping? And the answer is, you choose, and this is critical, you choose the mapping to E for, okay, so for a given computational setting, given the number of basis functions, the finite element mesh size, everything is given. The test problem is given. For that given computational setting, can we find the mapping that yields better results than the filter used by Lorey? All right. So this is a general form of the mapping. We choose different model forms for the mapping, like linear, like we have like an A tilde times, the coefficients A, the vector coefficient, or quadratic. That's something that we're very, as I've shown you last time, we're very happy with, or even machine learning. So there are three forms: linear, quadratic, these are very structured, or completely unstructured machine learning. And the question is, okay, we define the mapping. It's very general, right? Non-linear. How do we choose the parameters? And the crux of what we're doing is to use a PDE constrained optimization problem. This is in contrast to what I've shown you so far. What I've shown you so far was a completely unconstrained general type of optimization problem, like machine learning. Usually you minimize a loss function. We don't do that. We minimize the loss function. I mean, we do that. We minimize the loss function. However, we minimize it subject to the vector of coefficients A solves the corresponding ROM. So in other words, we say, what are the best parameters of this mapping such that when you take that mapping and you put it in this, is null array, is this modified Galerkin model, that Galerkin, that resulting model is the most accurate solution. So for us, the loss function is the difference between the form quantity of interest and the resulting stab up, whatever that is, quantity of interest. For us, it's kinetic energy, but could be something else. Here we have a regularization parameter. That's the usual machine learning type of approach. And once again, we're not doing this. We're solving this minimization problem subject to such that the vector of coefficients solves the resulting stab up ROM. So just to make things clear, this is Lorey ROM, and then stab up ROM. That's what I have there. Is gonna be exactly the same thing, with a little difference, this small difference. Okay, well, I would have to erase this. So this we have, plus instead of this, I'm gonna use this. So I'm gonna have an F of AR. Okay, dot, okay, this is in white, dot grad of UR. Comma VR is equal to little f times VR for all VR. So you see that the only difference between the two is the way we modify the convective term. That's the difference. Yeah? And this tab up ROM is what we use as our PD constrained optimization problem. Right? So we replace the filter with a machine learning mapping or quadratic mapping. So the question is, can we do better than Lorey? What do you think? Can we? Do you trust Thomas? Thank you, Thomas. Thomas was the only one who said yes. Oh, I'm very disappointed. Maybe online, some people, people had trust, had faith in us. But so far, I have to say, Thomas was the only one who's. This is very disappointing. So anyway, the answer is yes. Thank you, Thomas. You're right. So the answer is yes. I have to say that usually, we do this together. I was not super optimistic. It made sense, but I was like afraid. So I was so happy when we got good results. We got good results. So if we look at like the kinetic energy evolution, we have this for the different R dimensions, 6, 15, and 30 in blue, we have the Luray-ROM, and in black, we have the FOM. And we considered the linear, quadratic, and neural network versions. And for 6 and 30, we clearly do better than Luray. Clearly do. Here is not that clear, but if you look at, for R is equal to 15, but if you look at the overall, the mean square error of the kinetic energy, in blue, we have Luray, and pink, orange, and green, we have the linear, quadratic, and neural network. And look at this one. Look at the difference. The mean square error is 1.6 to the e to the minus 4. This is 1.5 e to the minus 4. Major difference. Then we said, okay, let's look at the kinetic energy. And you know, it doesn't look like a big improvement. But again, I want to emphasize this is a log scale. So those differences are significant, right? And this, we're zooming in here. When you look at the kinetic, the energy spectrum, in blue, we have the Luray-ROM, and in green and orange, we have the neural network and the quadratic versions, which work the best. The quadratic and the neural network work the best versions. Okay, it works. This is turbulent channel flow. We have results for the flow path, 3D flow past the hemisphere and the lead-driven cavity. So different examples every time we beat Luray, the spatial filter. Now, Luray cannot answer, but I felt very good that we actually get better results. Now, a natural question, and this is the second part, and I'll end up with this, is this is an operator, data-driven step-up, that works. For sure, that's how it's designed. For a given setting, we beat the standard filters. But the question is, how does this look like? Is this a filter, or is it something else? Right? That's a good question. So it's a data-driven operator, very general. We beat the Luray-ROM, but the operator itself, how does it look? It's not clear. So that's what we did. In this picture right here, we took a very noisy GROM field, and we did three things. First, we applied a differential filter in these three columns, this, and this, with different delta values. Then we applied the projection filter with different percentages of modes that we cut. And finally, the last three columns are the stab-up results for the linear, quadratic, and neural network approximation. And you can see that these results show that, right, we go from these noisy results to smoother results. So overall, the stab-up stabilization operator, data-driven stabilization operator, is smoothing the field. So it acts like a filter, but not always. All right. So there's some frequencies that are not damped, because you're asking me about frequencies. Yeah. So we cannot say that it is either the differential filter, because we don't get the same results, or the projection filter. And in fact, we cannot say that it always filters all the frequencies. Some frequencies are left unchanged. Overall, it does, right? So overall, if you look at the overall effect, it's smoother. It yields smoother results. So it's kind of a filter. It's a definite smoothing operator, but is different from any of these filters that that are used in practice, which I think is interesting. Huh? Okay, so final thoughts. So filters have been used for a century, starting with Jean Luray, maybe Stokes. Definitely they're used in LES, and I believe more and more, because they're very convenient, are going to be used in reduced order modeling. They're convenient. Practitioners, you know, graduate students, but most importantly, without any engineers can use spatial filters. Very easy. Right? Now, I'm very excited about the StabOp, the stabilization operator. It is goal-oriented, so I cannot say it's better than filters. What I'm saying is that I know that filters work for any type of setting. We're not doing that. StabOp says, give me what problem you're trying to solve. Tell me how many modes you're taking, what problem, lead-driven cavity, turbulent channel fluid, what problem you're doing, and then what the finite element discretization is. So tell me all these parameters, and for these given parameters, I find you the best mapping. It's different. If I change the problem, the filter is going to change as well. And in fact, that's what we're looking at right now. We're trying to find if there's anything common when you change, like, for example, the problem, or you change the dimensions, or, yeah. This is one thing. Now, I feel like this is like Jason Bourne. We went rogue. I mean, once again, it's like a religion. Filtering is a religion in LES. Like everybody believes in that. And we said, well, what if we don't use that? I think that this is interesting. And I want to emphasize this. It's also, I think of it as data-driven prosthetics. So the spatial filter is like you say you injured your leg, right? So you cannot walk anymore. I think in my mind, like filtering is like, using crutches, right? It helps you move around, or you bandage your leg, or you do things like that. This is different. It's not like you keep the Navier-Stokes, like filtering, keep the Navier-Stokes and massage the equations a little bit. You change the equations. So here, we're changing this term. We're replacing the Navier-Stokes term, clearly. Now, we don't have any mathematical analysis for that so far. We just started, right? It's a new paper. And once again, I think that the interesting part is to look at using different parameters, see if we can get something that it is common, a StabOp that is common to those. And another thing that we're interested in is how about using this for full order models? The same idea could be, applied to replace the usual LES filters or the regularized models. Why not use that? Yeah, it's gonna be more expensive. A PD constrained optimization, much more expensive, but that's something to be tried. And finally, I will say, remember when I said that my goal is to look at commercial software for fluids in 2030. I've decided to update my prediction to 2040. Okay, so we'll talk more about that then. All right, very good. So I'll stop here. If you have any questions, I'll listen to your questions. No, thank you. All right, thank you. Thank you. Ah, yes, Carlos. Yes, that would be. Yes, right. I learned my lesson. Okay, very good. Thank you, guys. Oh.
Yo creo que